Hi everybody, this is lecture 18. We're discussing section 8.1 again, sequences. This is our second day of discussing that section, which is our second and final day. So on Wednesday, the last part of the meeting, we'd started discussing what's called the continuity and convergence theorem, which says that if you have some sequence that converges to some number L, it's got to be a real number, and you have some function that's continuous at L, then in that special situation, if you have a sequence that's built up with an outer function and an inner sequence, and you take the limit, you can bring the limit inside. So this is by the C and C theorem. Tells you in certain situations you can bring limits inside of parentheses. And then that limit, of course, is the number L, so this would just be f of L. So on Wednesday we had three examples. First example, we had a limit, the sequence that converged using this theorem. The second example, we had a sequence that diverged. I think it oscillated. In the third example, we had a sequence that converged, but not because of this, it was because we used the squeeze theorem. So what I want to do today is I want to continue this line of discussion and I want to do an example So A does sequence secant A subscript n equals secant of pi over 2 minus 1 over n converge. Anybody have any wisdom about this? Well, let's just dive in. Notice this is an outer function. Is the secant function. In the inner sequence, is pi over 2 minus 1 over n. Let's see about the inner sequence. The limit as n goes to infinity of pi over 2 minus 1 over n. Anybody want to tell me what they think that limit is? Oh, this should be pi over 3. Pi over 3. Pi over 3. Pi over 3. What is that limit? Yeah. Yeah, because this term is getting closer and closer to 0, so this is the number pi over 3. And then notice that the outer function, which is secant of parentheses, is continuous at pi over 3. So we can do this limit by the C and C theorem. So that is the limit as n goes to infinity of secant of pi over 3 minus 1 over n equals, by the C and C theorem, I can bring the limit inside. It's a big thing in math, the idea of when you have some function and you have some limit on the outside, when can you bring the limit on the inside? And so we know that that thing in the middle is actually the number pi over 3. And we know that that's 1 over cos pi over 3. So that's 1 over 1/2, so it's the number 2. So the sequence converges, and then it converges to the number 2. Okay, B. Does this sequence, B subscript n equals secant of pi over 2 minus 1 over n, does that converge? Yeah, Jace?
No.
Can you say why?
As n approaches infinity, it gets closer to 0. Secant of pi over 2 would be 1 over 0.
Right, right. So let's check the limit of the inside is the limit as n goes to infinity of pi over 2 minus 1 over n, and that's the number pi over 2. And secant, the secant function is undefined at pi over 2. So we can't use the CNC theorem. Now, it might be that this limit's going to exist, but we can't get there by using the CNC theorem. Okay, well, let's just try something anyway. We're going to dive in. So the limit as n goes to infinity of b subscript n is the limit as n goes to infinity of secant of pi over 2 minus 1 over n. And that's the limit as n goes to infinity of 1 over cos pi over 2 minus 1 over n. Minus 1 over n. All right, so here again, we can't use the CNC theorem. Well, let's just make some observations. So n is getting huge and positive, because that's what this symbol means. Imagine what happens to this when n gets more and more positive. So what about 1 over n? Who wants to describe what's happening to 1 over n?
It's approaching 0.
And positive. That's crucial. Closer and closer to 0, but positive. Okay, so then what's pi over 2 minus 1 over n doing? Marcy?
It's getting closer to pi over 2 from the right side.
No, from the left side, from below. So I'm subtracting things. So all my terms are going to be less than pi over 2. So this is excellent that Marcy made that mistake, because that's the devil is in the details in these problems. So this is approaching pi over 2 from below. So what's happening to cosine of pi over 2 minus 1 over n? What's happening with that? Pi over 2 minus 1 over n is a number that's very close to pi over 2, but slightly less than pi over 2. So somebody who hasn't answered, tell me what's going on with cosine.
It's getting progressively closer to zero.
But qualify that. I've been always saying, you know, qualifiers. Getting huge, positive, closer and closer to zero, but positive, approaching pi over 2 from below. So you're saying this is getting closer and closer to zero, but qualify that.
Negative?
Who else wants to guess?
Getting very small and positive.
It's got to be. Annika gets the points for that because she made the wrong answer. But so what is 1 over cosine of pi over 2 minus 1 over n doing? I need some new hands.
It's getting cosine of pi over 2 minus 1 over n. Sorry, I'm blinking. It's becoming a really small number. I just want to over that.
Yeah, so what is 1 over that going to be? It's going to be a huge positive number, yeah. Notice when I'm doing this kind of stuff, I'm talking about numbers here. So this is saying, look at these numbers and imagine what's happening with these numbers when that's happening. So this is going to be a huge positive number. That's the thing, it's a number. So these are all my observations. So when n is getting closer and closer, when n is getting more and more positive without bound, these numbers are getting huge and positive. So what do we say about the limit? Marcy?
It's getting closer to infinity.
We just say it is infinity. To say that the limit is infinity means that these numbers are getting more and more positive without bound. Okay, now, I'm going to go over to the sideboard. And Gabriel's going to complain because I'm going to write in red. Oh, so what do we say over here? Sorry, Gabriel's going to get mad because I'm going back and forth, but I got to get my steps in. So we say that the limit diverges. It does not converge, but it diverges to infinity. Or the sequence diverges. So that's one thing, but how does it diverge? It diverges to infinity. We've had other sequences that diverge, that oscillate. So the sequences can diverge in different ways. So back to this board. Frick and Frack do this. Look how fast those dudes are. Round of applause for Frick and Frack. Infinity, great. Frick and Frack, they're so fast. They do another sequence. They do this, the limit of the sequence with a plus here. just because they're done. The other group is still working on all that nonsense, and they're doing this. The limit as n goes to infinity of 1 over cos of pi over 2 plus 1 over n. And so they get 1 over 0, and they get infinity. So smart. All right. That's that. Our method let's let Cn be secant of pi over 2 plus 1 over n. So let's do the limit as n goes to infinity of Cn. So that's the limit as n goes to infinity of secant pi over 2 plus 1 over n. Now, dot, 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 we get minus infinity. What the hell? So why would we get minus infinity? Well, let's go over here to the details. In this example, I have minus 1 over n. So how did that affect us? Well, n is getting huge and positive, but so this is getting closer and closer to 0 and positive. So that meant that this thing is approaching pi over 2 from below, because there's a minus sign here. You can imagine if there was a plus here, this would be approaching pi over 2 from above. Now look at this. Cosine was getting closer and closer to 0, but positive. That's because there's a minus sign there. You can imagine over there, there'd be a plus sign here. And this would be, instead of positive, would say negative. And so what's this thing doing? It's getting huge and positive. That's because there's that minus sign there. If we did this analysis on that example, this would be huge and negative, and the conclusion would be not positive infinity, it would be negative infinity. Now let's go back over here, because again, I want to get my steps in for the day. Remember, okay, it's going to work over here. Sorry, Gabriel. Let's look at a graph of these sequences. So here's y equals cos x. Remember, it goes through the point 0, 1, and it goes through the point pi over 2, 0, 0, and it goes through the point pi, negative 1. So the graph of, and it looks like this. It flies into that point horizontally. Here it comes in at a 45-degree angle. Then here it flies in horizontally. So the graph of y equals secant of x, that's 1 over cosine of x. Well, 1 over 1 is 1. So it goes through the point 0, 1. 1 over negative 1 is negative 1. So it goes through the point pi, negative 1. But look what happens in between. When x is pi over 2, there's a vertical asymptote. And these numbers are getting closer and closer, the y value is getting closer and closer to 0, but they're positive. So this graph goes up alongside the left side of that asymptote. Goes down alongside the right side of this asymptote. So that sequence, Bn, we're looking at numbers getting closer and closer to pi over 2, again, sorry, n is going to infinity, we're looking at points on this graph that are this. The y values are getting more and more positive without bound. And let's look at the graph. So this is points of the y values of Bn. Now let's look at the y values of Cn. Well, Cn, again, we're to the right of pi over 2. So the values of Cn are doing this. They're definitely getting more and more negative without bound. So let's go back to frick and frack. Because this kind of casual use of arithmetic and infinity, I'm always ranting about. Remember, if you remember from Calc 1, this red chalk, it's red because this is my actual blood that I've dyed this chalk with. This is a bad solution. It's written in blood. This is no good. Now, what if you say, well, I mean, this one's okay because they got infinity. It's infinity. Well, no. I mean, if you happen to get the right answer by a method that just as often is going to give you the wrong answer, it's not a valid method. The fact that they happen to get infinity means nothing. So this kind of solution on a quiz or exam is worth nothing because it does not convey how the limit works. The limit doesn't work this way because that way, just gives you the completely wrong answer sometimes. So you can't do this. The devil in these limit problems, in these convergence problems, is in being able to slow down and do this kind of detail. And you can imagine, I mean, you do that kind of thing for somebody, 1 over 0 equals infinity, and people say, yeah, I guess so. I've heard that too. You hear all sorts of stuff about infinity. But the thing is, to explain how these things really work, you have to think of them this way. There's really no other way around this kind of detail. But notice, it took me 1, 2, 3, 4, 5 steps of reasoning. Every one of those bits of reasoning is just thinking about positive and negative, big, close to 0 or not close to 0, and ratios. So you get better at this. Okay, so that's that. Meeting part 2. Today's topics are really cool, as opposed to the other topics that we've been covering, which are also really cool. Meeting part 2 is limits involving, or sequences involving E. So recall from calculus 1, what is this limit? Anybody remember what that limit is? Notice it's an expression involving a base and an exponent. The base is getting closer and closer to the number 1. Now what's 1 raised to any power? Just 1. All right, so that makes you think maybe this limit's just going to be the number 1. On the other hand, if x is a very, and x is getting closer and closer to 0 from above, if x is a small positive number, what's up with 1 over x? Alexandra?
It's getting huge and positive.
Huge and positive. So I have a base that it's not quite 1. It's a positive number. It's a little bit bigger than 1, and it's being raised to huge positive numbers. Think about what happens when you raise numbers that are greater than 1 to bigger and bigger positive powers, like 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. Wow, they go nuts. A number greater than 1 raised to bigger and bigger positive powers goes to infinity. So maybe this limit's going to turn out to be infinity. Maybe it's going to turn out to be 1. How do you know? Well, what does it turn out to be? Marcy, you had your hand up.
Isn't it E?
Yeah. It's the number E. Turns out this is a big thing. The fact that this limit does exist and it's not 1, it's not infinity, it's this weird number. This is irrational, which means it can't be written as a ratio of integers. And all we can say, and you also can't even write it as a repeating or terminating decimal. All we know is, E is between 2 and 3. E is roughly 2.718. All right. Example, are we on example 3 now? Yeah. Let's consider this sequence. A subscript n equals 1 plus 13 over n raised to the nth power. Does this sequence converge? Well, that means we want to think about the limit. So the limit as n goes to infinity of an is the limit as n goes to infinity of 1 plus 13 over n raised to the nth power. Now, this is going to make you mad. I'm going to do a trick. This is 1 plus 13 over n raised to the n over 13 times 13. I didn't do anything there. I just multiplied and divided by 13. But it's kind of magic. I mean, if this were Salem in the 1600s, I'd get burned. So this is a trick. Knowing to do this. And then now we're going to use a rule of exponents that this is something raised to a product. So I can raise it to one power first and then the next power. So I'm going to do 1 plus 13 over n raised to the n over 13th power. And then I'm going to raise that to the 13th power. There we go. All right. Now I'm going to do something else tricky. I'm going to do a change of variables. Let's let u equal 13 over n. So then, well, then n over 13, of course, would be 1 over u. And also, when n goes to infinity, u, what does u do? Approaches 0, but say more than that. From the positive side. I'm dividing 1 by a huge positive number. You should be noticing that it's very important to talk about when you're doing limits to approaching a particular real number, that you pay attention to whether you're approaching from the left or from the right. Okay, so when I do this change of variables, I get the limit as u goes to 0 from above of 1 plus u to the 1 over u, and that's all raised to the 13th power. Now look, I have a kind of a nested thing going on. So observe, we have an outer function. We have parentheses to the 13th power. and that's always continuous. And the inner sequence is 1 plus u to the 1 over u. And we know that this sequence converges. I'm sorry. Inner function. So here I was talking about a sequence. Now I'm talking about, we're going to turn this, the expression into a function of the real number u. So we have an inner function, and this inner function converges. This inner function, the inner function has a limit. The limit as u goes to infinity, as u goes to 0 of 1 plus u to the 1 over u, we've seen from that review of Calc 1, that's the number e. That's all review. Well, so that theorem that I presented over there called the continuity and convergence theorem, there's something like that for functions as well as for sequences. So that theorem can be used here. Notice I have the limit on the outside of these parentheses, but here I can use c and c for functions. To say that I can bring inside of the parentheses to the 13th power the limit, to bring the limit in. Limit as u goes to 0 of 1 plus u to the 1 over u. And that's the number e. E raised to the 13th power. So the limit of that sequence, the sequence converges, and it converges to the number e to the 13th. So there are lots of, so again, the sequence converges to e to the 13th. There are lots of, not lots of, there are some homework problems that you have involving this kind of thing. All right, there is a topic that's on my list of things to cover, but I'm not going to get to this. So meeting part 3. We won't get to properties of functions, properties of sequences. So I'm going to say we won't get to read the book. The book is very clear on this. It's very simple concepts. So properties that sequences may or may not have. We already had one of these on Wednesday. The idea that a sequence may or may not be alternating. That is, alternate sequential terms have opposite signs. But there's another property that functions may or may not have. They could be increasing or decreasing. And if a sequence is increasing or if it's decreasing, one or the other, the idea is these come under the umbrella of what are called monotone. To say something is increasing means it's always increasing, so it's monotonically increasing. To say a sequence is decreasing means that it's always decreasing, it's monotonically decreasing. And then we have another term discussed in the book, the idea of a sequence being bounded. All right, so let's do our quiz.